Okay, so I suppose you can see my screen, right?
Yes, sir.
And start writing P in the chat window, right? Okay, so last time we started the chapter. I think it was chapter 7, Laplace transform, and we had a few examples. And the main challenging thing we learned was the region of convergence. We should say domain, but domain, I mean, is a thing which doesn't convey the message. So region of convergence actually um, uh, is the challenge associated with the region of convergence is actually reflected by this name. So when you just call it domain, you don't get that thing. So we'll get more into this today. So this region of convergence will typically be um, expressed in a certain way, and we need to develop some notation for that. I'll try to stick to the textbook. So typically you will see uh, R for that purpose, right? Let me use some different color. So R will typically represent the region of convergence, and it will be a subset of the complex plane. So if it is of this form, right, and A is some real constant, this will be called A left half plane, right? Can you guess why he's saying A left half plane and not D left half plane? Hmm? Can you see that? I need actually to connect this. Why can't we say D left half plane, right? Because this one depends on the value of A, and A can be anything, right? So if we set A to 0, that is typically what is meant, and then you say, okay, it's D left half plane. So, and we discussed last time that when A is negative, the plane will look like this. And in both cases, yeah, regardless of whether A is to this side or to that side or somewhere here, the region of convergence is always to the left, right? That's why we call it the left half plane, A left half plane. And if it is of this form, yeah, all the values of S for which the real part is larger than some constant A, um, then then we'll call it the right half plane or A right half plane for each value of A. Okay, and one more thing, I mean, I have to repeat it every time. Although we are using symbols here, so S is also a symbol and A is also a symbol, but there's a difference. A, even though we don't want to specify the value, but it will still be a fixed number. Yeah, so it has to be a fixed number, and we don't care about the value. But S cannot be a fixed complex number. It has to be indeterminate. That's why we can label it here, right? So the nature of S and A are different. Okay, so now we need some notation to speak of the region of convergence, because region of convergence is a set. So you know how we represent the intersection of two sets. Um, so if, let's say, if you have one region of convergence R1 and the other is R2, uh, in this case we can see that this R1 is it is a left half plane because it is to the left of some fixed number. In this case, it's 1. And here to the right, you have another region of convergence, which is a right half plane because it's to the right of some fixed number, which in this case is -1. And if we now take the intersection of these two, it should be very clear that the intersection is this one. Yeah. So you can only have points which are common to both. And sometimes you need to shift a region of convergence. So let's say there is a region of convergence S, and you just add a scalar constant to each point of S. So this will be the precise way in which you write it. Um, the complex plane where each z, uh, you add a constant a to each z, and instead of writing this every time, you write it as this s plus a, right? Um, and this notation is only allowed when one of these two addends is a set and the other is uh, a number or an element of that set. Um, it should not mean that you start adding two sets. So let's say there is a set 1 and there is a set 2. So if you say S1 plus S2, there is no agreement in the mathematical community of what should we mean by this, right? So if you have a specific meaning, you have to clarify it. And yeah, but that's not something you should say. There are multiple ways in which this can be interpreted. So, but here, this will have only one meaning. Whenever you start with a set and you add an element to that, this is what we will have in mind, right? So it's a set formed by adding the constant a to each element of S. This is what. So an example is this. Let's say we have a region R, right? So let's say this is a strip, and we want to add 1 to it, plus 1. Yeah. So this whole region will be shifted to the right, right? Okay. So shifted to the right, and this must not be confused um, with this notation, right? Sometimes we have f of x, and if we say f of x plus 1, that graph actually shifts to the left. That is a different thing, right? That is shifting a function. Here we're not shifting a function. Here we're shifting a whole set. And there plus would simply mean shifting to the right, and minus would mean shifting to the left. Another convention which is typically used when reporting regions of convergence is that you can start with a set S and you multiply every element of that set by a constant A. So instead of writing this horrible thing every time, you just say, okay, AS. And I think I have been using this before as well, right? Even in the course of discrete structure, remember, if we have Z as the set of integers, and if I say 2Z, it means, yeah, even numbers, right? So we have been doing that before as well. And you can even divide, right? You can divide, let's say divide by 2 or divide by 3. So that is because A can be less than 1, so this notation works. And of course, you if A is positive, uh, you only get scaling, but if it is negative, you also have some. Yeah. Uh, if it is real and negative, it will have a reflection. But if A is a complex number, then you also have rotation, right? Uh, because there will be argument of A, and that argument can lead to rotation. So there are some examples. Let's say this is our original set R, the region of convergence. So this will be true R, and you can see easily that all points, yeah, in this region, every point has been multiplied by 2. So you can even trace it now. If I zoom this 2 becomes 4 because it gets multiplied by 2. And this negative 1 on this side becomes my negative 2 because it gets multiplied by 2, right? So it just stretches. And because this is infinite, so yeah, infinite remains infinite. And if you multiply it with negative 2, so and scaling, in addition to scaling, actually there is a flipping as well. So you see this negative 1 gets multiplied by -2 and it becomes 2, right? And this plus 2 gets multiplied by -2 and it becomes -4. So you see there is a flipping as well in addition to scaling. If it was a complex number, let's say if we had to multiply r with, let's say, 2 exponential minus j, yeah, let's say pi by 2, right? So then this minus pi by 2 is the argument, and then you would have a rotation as well, 90-degree rotation clockwise, so on and so forth. Okay, so now we need to learn a few things. This was the notation, okay? We now know how to represent the region of convergence, multiplying by a scalar, shifting by a constant amount, and intersection. These are the only three operations we'll need. So next we need to gather some rules. Okay, so typically now we are learning properties of ROC, okay? So the general form of an ROC means region of convergence. It will typically consist of strips parallel to the imaginary axis, right? So if you have a strip, this strip is parallel to the imaginary axis. So this is a valid ROC because the strip is now parallel to the imaginary axis. Why it's parallel to the imaginary axis? The reason is that um, convergence is determined by the real part. And if you apply some condition to the real part, it will either be less than something or greater than something. So you're not discussing what happens to j omega. That's why uh, there is no condition or no bounds on how large the imaginary part can be. Only the real part needs to be to follow some condition. So that's why an ROC could look like this, where you apply some condition to the real part, or it could look like this, but it could not look like this. Can you tell me why this is invalid? Because this places a condition on this
The
thought.
imaginary
Yeah,
axis.
and that is so now you will see why we choose the name ROC. Yeah, this could be the domain of something. This is a valid domain, but this is not a valid ROC, right? ROC is specific. It's a specific type of subset. It's not just any subset. Now, and the reason the strips looks like this is that if you have any point S naught, so I'll just pick any point S naught, for example. Let's say this is S naught. And if this is an ROC, then the vertical line through S naught. So if I now choose a vertical line through S naught going all the way up and down, this will also be an ROC because you're not changing the real part, and only the real part has to respect certain conditions. So you should be able to identify which regions in the complex plane uh, form valid ROCs. Okay, so this is strips. Okay, um, I wouldn't say all, but most of the Laplace transforms. And by now you should understand that whenever we get Laplace transform x, it will be the transform of some time domain signal small x, and we will have this relationship, Laplace transform. Um, and sometimes we can have that indeterminate as well. So if we promise that we will always use t for the indeterminate, uh, and we'll always use s for the indeterminate, this is something you have to fix. Because if you think of this not as an indeterminate but as a real number, then you have the freedom. You can choose a or yeah w. But when you want to have it as an indeterminate, then you have to fix it. Otherwise, the reader has no idea. So we typically fix the indeterminate to t, and we fix this indeterminate to s. So now the thing is, Okay. Um, in most cases, if you can recall it from some previous courses, the Laplace transform will be will be in the form of a rational function. You will have some polynomial in the numerator and some polynomial in the denominator. And you will also remember that that can be factored as well somehow. You can have these factors as well, right? Because any polynomial can be factored. So whenever the Laplace transform is a rational function of this form, okay? Rational function. Rational function mean that the numerator will be a polynomial and the denominator will be a polynomial. Then the ROC does not contain any poles. Remember, poles are actually values of s corresponding to these factors in the denominator, right? So if I have, let's say, s plus 1, and in the denominator I have s plus 2 times s minus 3. So can you now tell me what are the poles here? Where are the poles?
Minus 2 and 3.
Minus 2 and plus 3, right? They are the roots of the denominator. So now can you tell me why he says that the ROC of x does not contain any poles? What is the justification of this thing? Why does not? Because ROC means region of convergence. And you know at the pole, this transform does not converge, yeah? It becomes infinite, right? So it cannot contain any poles, right? It can contain 0, it can contain any other point, but it cannot contain 0. The other thing, and it's bounded by poles or extends to infinity. There are two possibilities. It will either be bounded by poles, and the reason for this is that we have seen conditions like this. The real part of S greater than A. So you see, you bound it from the right side. And when you say real part of S is less than N, you bound it from the, because these are the only possibilities, so it will be bounded by poles. Yeah. Or extends to infinity. When there is no bound, it will extend to infinity. There is no third possibility. So we will now identify valid. So can you now tell me why is this valid? By applying this shape. Hmm? Why is this a valid ROC? Hmm?
Um, these are the poles excluded from the region.
Yeah, so it will now highlight everything which is true here, okay? So I'm now using different color, right? Sorry. So it does not contain poles. What are the poles here? This one, and this one. You typically use cross, yeah? So there are three poles, and the ROC does not contain those poles because the shaded region, right? This is the ROC, and it doesn't include it. The other one, it must have either this or this. So which one is true here?
Bounded.
Bounded by poles, yeah? So you bound, the region is bounded from the left by this pole, right? And it is bounded from the right by these two poles. So that's why it is a valid ROC. What is the third thing which makes it valid? And I want you to pick that thing from the previous slide. Hmm?
It doesn't depend on the magnitude, imaginary axis.
Yeah, so it's a vertical strip, right? You see, we saw that. It must be a vertical strips, not one strip, not necessarily one strip. You can have multiple strips, right? Parallel to the imaginary axis. So it satisfies all the requirement. It is a vertical strip. You can have more than one strip as well. In this case, we just have one, and it satisfies this. And remember that this will only be the case when you are dealing with a rational function. So these examples are actually, you read, pay attention to the statement. valid ROCs of a rational Laplace transform. The moment I remove that condition rational, then I don't need to have this property. Okay, why is this valid? Tell me. Vertical strip, right? Bounded from the left by these two poles, right? And what happens on the right?
Infinity extends to infinity.
Extend to infinity, yeah, because he stops at the arrow. There isn't, I mean, you can't draw it everywhere. So now tell me, why is the last one invalid? Hmm? What makes that one invalid?
It is bounded.
No, from there is nothing wrong with this one, yeah. This one is fine, right? It is bounded from the left by poles.
Right side pole is included in the ROC.
Sorry,
I think right side pole is
there is no
included.
pole on the right side. The pole is only a cross. That is not the reason. It is bounded by what? It is bounded by what?
Strip.
Yeah, by a strip. It is not bounded by a pole. Yeah. So what does it say? It will either be bounded by poles, and when there are no poles, it must extend to infinity, right? So because there is no pole, so to make it valid, this part must extend to infinity, just like this. So there is no way you can have a bounded, yeah? You cannot bind an ROC by regions other than poles. Pole is the only mechanism of bounding a LROC. Do you get that?
Mm.
Yeah. So if I, just to make sure that you follow it, what if I had no poles? What if I remove this? Okay. Let's say I remove this. So how should this ROC be? It has to extend to the left as well, right? So then the entire S plane has to be ROC, right? Because you can only have this binding if there are poles. So make sure you understand this point, right? Okay. Uh, Now there is another finite duration functions. So before you can imagine, can you recall one-sided functions? What do you mean by one-sided functions? In time domain. Let's say in time domain. So let's say I have x of t and it is one-sided. What does it mean?
Causal anticausal,
Hmm?
like causal anticausal functions.
Yeah, causal, anti-causal is a special case of that. This is a general concept. One-sided means that if you have a function, right, and if you graph it, there there must be a point, right? That point can be anywhere. Let's say, let's have it here, where the function must be zero to the left of it. So it must be zero here, right? And it can be anything here. So I don't care what happens here. Whether it's zero or not, I don't care. One-sided, and one-sided actually is not a good word. You should say right or left, okay? So right-sided, because one-sided is not clear, right? So what do you mean by a right-sided function? When it must be zero below a point and that point must exist. This point can be negative, it can be positive, it can be zero. When it is zero, then we call it, just as you said, a causal function, right? So the focus is on this part. You don't care what happens here, right? So what will be a wrong way of defining a right-sided function? That is very subtle, but that will be wrong. If I say that right-sided function is a function which is non-zero to the right of a point, because now I'm focusing on the non-zero. That is not the focus. The focus is this. Do you see the difference between these two perspectives? Why am I saying that? Okay. If I fix it to the non-zero, then let's say if it is zero everywhere, right? Let's say I have a function which is zero everywhere. So by if my definition is focusing on zero, I don't care what happens here. So this will still be a right-sided function, right? Not because of this, but because of this. I hope you get the point, right? What will be a left-sided function, if you can recall? Hmm? What will be a left-sided function? There are some stupid shortcuts, and I'm not aware of those. That actually disturbs everything. So there must be a point, it can be here or anywhere, such that the function is zero to the right of that, right? And I don't care what happens here. It is zero, non-zero, I don't care. So then we will call it a left-sided function, right? So what you can say, oh, it can be non-zero at the left-sided. Right-sided can be non-zero. It doesn't must. You don't say must be. So what um, will be a finite duration function then? Can you now tell me what will be a finite duration function? If hmm?
Bounded by both sides.
Yeah, it must be bounded by both sides. So it means that it must be, don't say bounded, it must be zero above some point, right? And below some point. So there must exist 2 points, right? So that it is zero above one of them and it is zero below one of them, and you don't care what happens inside, right? Is zero, non-zero, you don't care. So this will be a finite duration. Can you now tell me that if you have a finite duration signal, is that left-sided? Is that a left-sided signal? Yes or no? Just try to apply the definition. What when I reminded you, what do you mean by left-sided? That it must be zero to the right of some point. Yes, so there is a point and it is zero there. That's all you care. So it means that every finite duration signal is automatically a left-sided signal because I'm only interested in this zero. Can we say this is also a right-sided signal, this finite duration signal? Yes or no?
Yes.
Yes, right? Because all I care is that there is a point below which or to the left of which it is zero. So it means that a finite duration signal is a left-sided and a right-sided at the same time. It doesn't mean that it's two-sided, right? That's the misconception. So what will then be a two-sided signal?
Not bounded to any side.
Yeah, so it's not bounded by any side. So it means that there is no point beyond which yeah it is bounded. So now we have three. So to fix this concept, we need now a table, right? Let's have a table, and you will now see how to clarify this. So let's say we write here uh, left-sided, and then we say right-sided, right? So we can say, okay, yes, yes. So what name can we use here? An alternative name,
Finite duration.
finite duration, right? This will actually make sure that you know what you're doing. Let's say this is yes and this is no. What will be your choice of word for this?
Right-sided.
Yeah, this is what I was also saying, but there is a catch. When you say right-sided, finite duration is also right-sided. So how to make sure that you don't confuse it with anything else? You must say right-sided, but not. You have to say it explicitly if you want to make it clear, right? So saying right-sided is not enough. You must say right-sided, but not. You can have it in bracket or whatever in whatever form. So this is the only way to distinguish it from a finite duration signal. And now what will be this?
Left-sided but not right-sided.
But not. The reason I'm saying this is that we will now learn something about ROC and we have to make it very clear. And you should be able to plot this as well. So what if I have both of them no? What will be your word for this?
Two-sided.
Two-sided. Yeah. Without this understanding, there are many people who would think that this is also two-sided, right? But that will be a wrong understanding. So finite duration, which means that it is, you can simply say both. You can now say it's both right-sided and left-sided. And two-sided is not what we mean by that. So now let's get back. And now, if a function x, and by that we mean the signal in time domain, right? If it is a finite duration and its Laplace transform x converges for at least one point, if it turns out that it converges for one point, then it converges for all points in the complex plane. You can actually prove this very easily. And the reason you can prove this is that when a function is finite duration, you cannot have any issues of convergence, right? But why does he say this? The issue of convergence will not be because of duration, but it will be because of the function itself. Maybe the function has some weird behavior, right? Normally we don't have such functions, and that's why finite duration signals, for all practical purposes, will have the entire its complex plane as the ROC. Yeah, because the integral of the Laplace transform will converge. You don't need any damping. You don't need, yeah. So that's why uh, this is a valid example of a finite duration signal. Why is this invalid if the signal x is finite duration? Hmm? If you happen to know that the signal x is finite duration, why is this invalid for that? ROC. Hmm? It means you didn't understand this point, right? What does this say? That the entire complex plane has to be the ROC. This part is missing here, right? So it cannot be valid. Why? Because we know x is finite duration. Why is this invalid, right one?
Again, not the entire plane.
Yeah, it has to be entire, okay? So you have now learned your first rule. Of course, these this is not the first rule. I mean, we started with the property one. Property one means that the ROC has to be in the form of strips, one or more. Second property says that it cannot contain any poles. and is bounded either by poles or it must extend to infinity. And the third property is that if x happens to be finite, okay, sorry, for property 2, you must state clearly that it applies to rational functions, right? If the function is not rational, then this doesn't need to hold. So the first property is for any type of function, right? There is no condition. You can have any type of function, and the ROC must be in the form of strips, one or more, parallel to the um, imaginary axis. Property 2 is about rational functions. Property 3 is about finite duration functions. So without that condition, this property cannot be required to hold. Now, the fourth property is about right-sided functions. And we just said it. What do you mean by right-sided functions? Can you recall?
Right-sided but not left-sided.
Right-sided but not left-sided. What we mean by that is that there must exist a point on the time axis, right? Below which it must be 0, right? This point can be anywhere, and we don't care what happens there. So if a function is right-sided but not left-sided, he has to make it very clear here, right? Then the ROC is actually a right half plane. And this is a generalization of what we learned last time. If you remember last time, we had two examples. One was a right-sided function, but it was not left-sided. And the other was a left-sided function, but it was not right-sided. And we saw that because of that right-sidedness, the convergence, the ROC was of a specific form, right? That sigma was required to be larger than some value. So now, can you tell me uh, that if this ROC is valid, what type of function small x are we talking about? Right-sided or left-sided? Hmm?
Right-sided.
Right-sided. So if small x is right-sided but not left-sided, the ROC must be of this form, right? Okay. And why is this invalid for that same x? Why is this invalid? Now we have a function which is the right-sided but not left-sided. Because this is left, it is a left half plane, and we require a right half plane, right? And this one, why is this one invalid?
It's left-sided also.
No, you say something about the ROC. The ROC must be a right half plane. So this is a left half plane, right? When it is a left half plane, it cannot be a right half plane, right? What is this? Why is this not a left right half plane? Hmm?
Left-sided भी include हो रही है.
Yeah, but the question, I'm not asking a question about small x. I'm asking a question about ROC. ROC is required to be a right half plane. Why is this not a right half plane? What is the requirement for a right half plane?
Infinity को approach नहीं कर रहा right side से.
Yeah, that is the thing, right? So it must extend to infinity. It must if it was right-sided, if it was right half plane, it must extend to infinity. So it must be of this form. The real part of is greater than some number, right? Now, how about this one? If we have a function which is left-sided but not right-sided, the ROC must be a left half plane. So why is this valid? It is a left half plane. Why is this invalid? And
Not
yeah,
mhm.
it does not extend to
Infinity.
negative infinity, right? The requirement for left half plane is that it must extend to negative infinity. And why is this invalid? Because it's a right half plane, right? And right half plane cannot be a left half plane. Now we get to two-sided functions, right? Okay. Before I get to this, let me go back to a blank page and ask you something. You should be able to recall it from calculus, right? In calculus, I think if you recall, function, what was that? When you studied functions and combined functions, I think it was combined functions or something like that, right? Like when you take one function and then you take another function, right? And you add the two, for example, or you subtract, or you multiply, right? Can you recall how the domain is determined? Let's say you know the domain of f1, yeah? So domain of f1 and domain of f2. What would be the domain of f1 plus f2? Hmm?
The intersection of their individual domains before
Intersection,
it.
intersection, right? Similarly here. So any combination use must be in the form of intersection. Yeah? But there are some operations like f1 divided by f2 that it's not just the intersection, but you also have to exclude points for which it is undefined because of division, thing like that, right? So keep that in mind, right? And now we get to this. You should be able to justify this rule, property 6. Property 6 says that if x is a two-sided function, and what does that mean? That it is neither left-sided nor
Right-sided.
neither left-sided nor right-sided, right? So actually it extends to both sides, right? It extends to no, our extension is the word used for ROC. So neither left-sided nor right-sided mean that it can be I would say it can be non-zero on one side or the other side. So then the vertical line is in the ROC and it will consist of a strip in the complex line. So it must be in the form of a strip, a single strip. So it must be in the form of a single strip. Of course, this is not a single strip and this is not a single strip because it extends. So how can we justify that it must be in the form of a single strip? By using that idea of the intersection I just shared a while ago. Hmm? You can actually combine two functions. You can imagine it, yeah? You start with a left-sided function and you start with a right-sided function. And you can combine them in such a way that you clip them, right? No, you do not clipping them. You just take a piecewise function, right? So if I say, let's say there is a function, let's say that I have a function f1 which is right-sided, and then I have a function f2 which is left-sided. And now I define a new function by making it a piecewise function, right? So I'll say, okay, f1 when f1 is non-zero, right? So points where if 1 is non-zero, I'll take if1. And points where if 2 is non-zero, or I would say when if1 is 0, right? When if2 is 0, take f1. And when if1 is 0, pick f2. This function by design is two-sided, right? You get that? Because we make sure that it doesn't get 0 like these two. So you can you are actually making a combined function. And if the ROC of this is, let's say, R1, and if the ROC of this is R2, the ROC of this has to be R1 intersection R2. And now we know what will be the R1. What will R1 look like? It will be a right half plane, right? And this will be a left half plane. So when you have a right half plane and a left half plane, and you take the intersection, how will it look like? Hmm? It will look like a strip, right? You see, this is how a right half plane looks like, and this is how a left half plane looks like. Take the intersection of the two, and you get a finite strip, right? That's the justification for requiring the ROC of a two-sided function to be uh, in the form of a strip. So this is invalid because it is not a strip, and this is not invalid because it is not a strip. Okay. Um, property 7. I think property 7, before property 7, um, yeah, I mean, we should be able to understand it without a particular example because the diagrams are already given. So again, let's say you have, imagine a function small x which is rational, right? And rational with at least one pole. There are some poles. It can be one pole, more, two poles, three poles. And there are some rules. So if this x happens to be a right-sided signal, the ROC, we know the ROC will be a right half plane, right? So that is what we know. It has to be a right half plane. And because it cannot contain poles, so it has to avoid all the poles. So naturally, it has to be the right of the rightmost pole. So let's try to understand this point. And we have this valid example, right? X happens to be not, I think it's this, no, it's not this one, because he has these four figures based on this. So this is to the right. So these two figures actually correspond to this part, and these two figures corresponds to this part, right? So we focus on that last one, or this one, which is valid. Now, because x is right-sided, you have a right-sided function. So if it is right-sided, the ROC has to be a right half plane, right? So this is a right half plane, yes. Because it extends to positive infinity. And we can see that it is to the right of the rightmost pole. There are three poles, right? There are three poles. Why does it need to be to the right of that particular pole, which is the rightmost? Why not these two? How would you explain that? Hmm? Proof by contradiction, right? So let's say that we allow this to be to the right of these two planes. How will this look like then? And what will be a problem with that? We have made it a right half plane, right? It is a right half plane. So what is wrong with that?
So it will also be bounded by the other side. Shouldn't be like open from one side.
No, bounded is not the issue. The issue with this figure I have now drawn is that it now includes,
Another pole.
then that is not allowed. We must not forget the first rule, right? So the only way you can avoid violating the first rule is that to make sure that it is to the right of the rightmost pole, right? You have to respect all the rules. That is the only way in which you can respect all the rules. And what rules are we talking about? We must avoid poles, right? We must respect the rule that if a function is right-sided, the ROC has to be a right half plane. So this is the only way. It has to be a right half plane. It has to be a vertical strip. Yeah, all the rules. Now, why is this invalid for that type of function which is right-sided? Yeah, it's exactly what I said. Yeah, it includes this one. That's one violation, and the other is that it's not to the right of the rightmost. It is actually the leftmost. So whichever way you explain it, that's wrong. So let's get to the other one. And he is telling you that you can actually derive this rule from properties 1, 2, 4, and 5. Actually, it's combined all the properties. Now let's get to the second point. What if small x is a left-sided signal? The ROC must be a left-sided signal, right? But it has to be to the left of the leftmost pole this time. So let's focus on this part now. We have a signal which is left-sided, right? This x is left-sided. So the first requirement is that we need it to be a left half plane. So it is a left half plane, right? It is also a left half plane. But why is this valid and why is this invalid? Hmm?
Left of the leftmost pole.
Yeah, leftmost. And why leftmost? Because if we allow this, then it has to include the poles as well. And we cannot have poles inside ROC. So I think most of these rules you can actually reconstruct in your thought rather than memorizing. So now we have a general form of ROC. It's actually the same table which we just discussed a while ago. So if it is neither left-sided nor right-sided, it means that it is a two-sided, right? Neither left-sided nor right-sided mean two-sided. So if it's a two-sided signal, the ROC must be a strip. We just saw it. If it is right-sided but not left-sided, the ROC must be a right half plane. If it is left-sided but not right-sided, ROC must be a left half. And if it is both left-sided and right-sided, which means that it is said
Finite interval.
finite duration in time, right? Then the entire ROC has to be, sorry, the entire complex plane will be the ROC. So we now learn that if the transform exists, the Laplace transform, the ROC can only be, it will either be a left half plane or a right half plane or a vertical step or the entire. These are the only four possibilities. There is no other possibility. So now you are going to tell me what makes this one uh, invalid. Hmm? Why is it invalid? Check it. Is it a single strip?
No.
No. So this fails, right? Is it right half plane? No. Is it a left half plane? No. Is it the entire? No. So it fails every test. How about this one? We need to work it out again.
2 strips.
Huh?
There's 2 portions, not one continuous portion.
Yeah, so it's actually, it extends to this one, it extends to this one. So we cannot say it's a single strip, right? We cannot say it is a right half plane, yeah, because right half plane would mean that it's only that part. Left half plane would mean that it's only that part. So you can easily see that. I mean, all it has to be one of this, one of these four, and it's none. Okay, let's have some example, right? Oh, I would like to have at least one example before I get to the properties. Okay, so that's one. So he's now asking you to look at this Laplace transform. Imagine somebody has done it for you. He started with a small signal x, sorry, with a signal small x. He worked out the Laplace transform. You get the algebraic expression, but you know algebraic expression is not enough, right? Algebraic expression is not enough. You must know the ROC. So the ROC depends on small x, right? So he says, okay, identify all possible ROCs of this capital X. For each ROC, indicate whether the corresponding X is left-sided. So you don't know whether small x is left-sided, but not right-sided, right-sided but not left-sided, two-sided or finite direction. So we need to explore all the possibilities. So before that, let's factor the denominator, right? So these are complex poles, so we factor these two. These two are real poles, so vector this. So we are now having the poles. So let's have the poles here. Okay. So this one is a 0. So we just have a 0 here. And S minus 1 is one pole. S plus 2 this pole. This will be S plus 1 minus J, right? And it will be S plus 1 plus J. We have we have 4 poles and 1 0. So we start with this one. Let's assume that X is right-sided but not left-sided. Let's say we assume this one. Yeah. If this is the case, how should ROC look like? Tell me. What is the first thing we can say? If it is right-sided but not left-sided, ROC must be a right half plane, right? And right half, not only right half plane, it must be to the right of the rightmost pole. Which one is the rightmost pole? This one, right?
Mm-hmm.
So the ROC must be this one, right? Agreed?
Yes.
Okay, now about the second possibility. Let's redraw this line. And now we imagine that X is left-sided. Sorry. X is left-sided, but not right-sided. Left-sided, not right-sided. So what can we say about the ROC?
To the left of -2?
Yeah. It has to be a left half plane, and to the left of the leftmost. So this one, right? Yeah, clear? Okay, let's look for the other possibilities. How about two-sided? Let's say it is a two-sided function x. What is the first thing we can say? It must be a single strip, right? Must be a single strip. The next one, so it means that it cannot be extended to the right or to the left, and it cannot include any pole. So can you now imagine where the strip will be? Can we have a strip here? Here? Hmm? Let's say I claim that this is the ROC. What will be wrong with that suggestion? Hmm?
including poles.
No, but I'm avoiding poles. I'm not crossing. This region I shaded avoids all the three poles, and it avoids the fourth pole to the right as well. What is wrong here? Hmm?
सर ये तो ना लेफ्ट हाफ प्लेन है ना राइट हाफ प्लेन है हम बोथ साइडेड इसलिए
It is a strip. It is a strip. You are ignoring zero, right? What does zero mean? Zero किसको हम कहते हैं जिसमें लैपलास ट्रांसफॉर्म की वैल्यू क्या हो? You forgot the meaning of zero, right? What do you mean by zero? Okay, when I replace s with this value, x of s should be बताएं?
1/2.
No, 1 by 2. S,
0.
S, that is why we are calling it zero, that x of s has to be zero. So जब x of s zero है तो वो कन्वर्ज करेगा या नहीं करेगा? जीरो पे जो चीज पहुंच जाती है आप कैसे कह सकते हो कन्वर्ज नहीं कर रहा? And your ROC suggests that zero is outside that, right? So it must converge here, right? बात समझ आ रही? That must be included in your ROC. So ये मतलब कि गलत हाइपोथेसिस था. अब आप सजेस्ट करें कहाँ होना चाहिए? स्ट्रिप उसने होना है तो इसका मतलब ये है कि वो स्ट्रिप यहाँ पे होगा, राइट? कहाँ पे होगा ये, राइट? अब इसने उच्च पोल को भी अवॉइड कर दिया, इन दो को भी कर दिया, राइट कर दिया और जीरो बेस में आ गया, ठीक है? एंड इट्स अ सिंगल स्ट्रिप, राइट? So you need to use some thinking to actually. All you need to do is to satisfy all the requirements, right? Now, how about the last one, finite duration? Hmm? बताएं
ऑल
why
पॉइंट्स तो नहीं हो सकते ना, ऑल प्लेन तो नहीं हो सकता.
वो हो ही नहीं सकता ना, क्योंकि आप ये चार पोल्स के साथ आप क्या करेंगे, ठीक है? So that's not a possibility, right? I think this simple example should be enough to teach you many things, right? Let's get to the lecture slides again, right? properties. So now you need to tell me, of course, we're not going to derive these properties, but you are going to tell me the justification for each one of them based on what we learned so far. Linearity, right? So if I combine two functions linearly, the Laplace transform must be combined in the same way, of course. This means the Laplace is a linear operator. So if R1 is the region of convergence of x1, right? And if R2 is the region of convergence of x2, I would expect, because this is a combination, so I would expect this to be an ROC. Why do you think he says at least? What is the reason behind that? Why not simply R1 intersection R2? Any idea? At least का मतलब क्या है कि इससे larger होगा या इससे smaller होगा?
Larger.
हाँ, so why does he allow that it is possibly? हमें चूंकि x1 x2 का नहीं पता ना, तो हमें ट्रांसफॉर्म का भी नहीं पता. आपको याद आ रहा है कि जब आपने लेप्लास ट्रांसफॉर्म टू रैशनल फंक्शंस को आप ऐड कर रहे हैं, ठीक है, इसके भी पोल्स होंगे, इसके भी पोल्स होंगे, ठीक है, and we are adding two rational functions. What is possible here? What can happen to some of the poles? इसकी जीरो यहाँ होंगी ना, इसकी जीरो इधर होंगी, पोल्स इधर होंगे, यहाँ पे इसकी जीरोज होंगे. तो आपके ख्याल में यहाँ पे क्या हो सकता है पोल्स के साथ? कोई एक पोल गायब हो सकता है इधर?
हो सकता है.
फिर कैंसिलेशन हो सकती है ना.
हम्म.
Whenever you are combining two rational functions, it is possible. Of course, it will not happen always, but in some cases, it is possible that one of the poles gets cancelled by a zero because you are combining. So इसका मतलब है कि उस केस में फिर वो जीरो, वो जो पोल है वो भी आ जाएगा और आपका जो ROC है वो बेसिकली बड़ा हो जाएगा, right? So that's what you need to keep in mind. This will be the case whenever you combine functions. Okay. How about time shifting? How can you justify this one? And remember, R is the region of convergence of X. तो शिफ्ट करने के बाद ये इस तरह से चेंज हुआ है. अब मुझे सिर्फ ये बताएं कि इससे ये रीजन ऑफ कन्वर्जेंस चेंज क्यों नहीं हुआ? इससे फर्क क्यों नहीं पड़ा इसको? हम्म? हम्म? इमेजिन शिफ्टिंग ऑपरेशन, शिफ्टिंग से कन्वर्जेंस पे फर्क पड़ना चाहिए. लेप्लास में लिमिट्स क्या होते हैं आपके? माइनस इंफिनिटी टू प्लस इंफिनिटी. तो अब अगर मैं शिफ्ट करूं तो अगर वो कन्वर्ज जहां पे करेगा फिर भी करेगा ना, वो शिफ्ट करने से वो कन्वर्जेंस तो चेंज नहीं होगी ना. वो लिमिट वैसे भी आपने माइनस इंफिनिटी टू प्लस इंफिनिटी लिया हुआ है, तो आगे पीछे शिफ्ट करने से कोई फर्क नहीं पड़ सकता ROC पे, राइट? सो दैट्स व्हाई इट रिमेन्स द सेम. और दिस इज शिफ्टिंग इन लेप्लास डोमेन. अब यहाँ पे क्या, यहाँ पे चेंज हुआ है. R के साथ आपने क्या ऐड किया है? रियल पार्ट ऑफ S नॉट. सो नाउ टेल मी, व्हाई शुड आई ट्रस्ट दिस रूल? इसका बहुत आसान रूल है, ठीक है. अगर ये x of s होता, ठीक है, if it was x of s, so what do you mean by ROC? If ROC is R, so we require S to be, or to belong to R, right? S must belong to R. So how should that rule change when the Laplace is x of s minus s naught? Now s minus s naught must belong to R, right? Agreed? Because you say that the Laplace transform is x of s minus s naught. So when s minus s naught must belong to R, s is a fixed number, s naught is a fixed number. This means that s must belongs to R plus s naught. Bring it to the other side. But remember, s naught is a complex number and convergence only deals with the real part, right? So convergence will take only the real part of S naught, and that's why it is R plus real part of S naught, right? Imaginary इसका जो imaginary part है वो it is irrelevant है for convergence. And similarly, you can explain all these other things. Yeah. So S over A. Yeah. So S over A must belong to R. So S must belong to A times R. That's why it is A times R. And A times R mean multiply each point of the region of convergence. Same goes with this. Yeah. Convolution. Convolution is also a combination. So it will be at least R1 intersection R2. Differentiation doesn't change. Oh, differentiation can make the ROC larger, at least R, right? And the reason is this, because differentiation corresponds to multiplication by X, by S. It is possible that capital X has a pole S, and this actually cancels it, right? So because cancellation of poles is possible, that's why it's at least R. And similarly for integration, right? Integration corresponds to dividing by S, and dividing by S here requires an additional pole, and because real part of S must be positive, so now you have this. It's just the same rule, right? R1 is for X, R2 is for this one, and then you take the intersection. So it's actually an application of that intersection rule. Is there any question in these properties? So you must not only be able to apply these properties, you must be able to explain these properties as well. This initial value theorem and final value theorem, I think you have seen this probably in the course on differential equations, where the initial value from the right, x of 0 plus, you know what we mean by x of 0 plus. It means limit of x of t time when t approaches 0 from larger values. If you apply this to the inverse transform, you'll get this thing. You can prove it yourself, right? You just write the definition of the inverse transform. Oh, did I write the formula for the inverse transform last time? I think I didn't write the formula, right? So you must be able to write that formula. And because you have taken CVT as a course, so I don't see any problem you understanding the formula. So the Laplace transform of x of t, if we write x of s, and if you say, okay, it will be a function of s. So it is actually from minus infinity to plus infinity, x of t exponential minus st dt. And we know this was actually a modification of the Fourier transform. And the inverse transform will look like this: small x of t, the inverse transform of x, capital X of s, and then the whole thing being a function of t. This integration has to be in the complex domain, so it will be ds here, right? And you have to integrate x of s, and it has to be opposite to that, so it will be plus st. And here, because of its connection to Laplace transform, you have to write 2 pi j, right? And this, you cannot say minus infinity to plus infinity. What is wrong with these limits? Can somebody tell that? Why can't I write minus infinity to plus infinity just like I had it there? Because S is complex, right? So the limits must be complex. So actually, instead of having complex limits, you just say it's a contour integral. It's a contour. And this contour in S plane, it has to be a closed path, contour C. this path must avoid all the poles, right? Any poles you have must be outside, right? No, inside, sorry. I think it's inside. I just said the opposite way. So this contour has to be it has to include all the right half plane poles.
They can be on the boundary as well, right? Of the contour.
I think you have to avoid you have to enclose, Cauchy's integral formula, right? Because you will
Yes.
be using residues and that requires poles to be encircled. Because if you cross the pole, then you cannot have convergence, right? Yeah. Do you remember the Cauchy's integral formula? So if you have any poles inside, it will just be the sum of residues, right? And each pole will have a corresponding residue. You don't need to worry about this integration because you will have Laplace transform tables, right? So when you have tables, you won't need this integration. This integration was only needed in that course, CVT. So you will not have to apply that integration. You just need to be aware of the integration for conceptual reasons, not for computation. Computation will require you to use properties, right? And similarly, final vary theorem. So if you try to prove this, this will apply, the limit has to s approach infinity. Do you see anything wrong with this limit? He has done it, but this is not in line with how we will write it in CVT. How should this limit be expressed more correctly? You are in S plane, right? So when you say S approaching infinity, infinity typically means real infinity, right? This one. So this is not what is meant. This means anywhere, right? So this has to be written in such a way. So a better way will be to say the modulus of S approaching infinity. So actually you are now referring to that infinitely large circle, right? S has to be anywhere. And that is correct because 0 is the origin, so you can approach 0 from any side. Okay, let's discuss some of these transform pairs. Write the P in the chat window again, right? Because we are getting near. Can you quickly justify this first entry? Justify it in two ways, right? First, justify it without deriving it. How should I trust this ROC in this case?
Because you're only getting a spike at one point, so.
No, use the language of properties. ROC all of S. When was this the case? There were those four types of functions, right? Right-sided function, but not left-sided, left-sided, but not right-sided. Yeah, finite duration, and then two-sided. Which one of them is here?
Finite.
Finite duration. Yeah, so it has to be that. So you should be able to apply this rule to any. Yeah? So let's say, how will you justify the second entry without doing any math? U of t is right-sided, but not left-sided, right? So this must be right half plane, right? And it must be to the right of the rightmost pole. Where is the pole of this? You see it here. Where is the pole? Can you see the pole in the S-plane for this case?
At 0.
At 0. So now this makes sure that the ROC is not only right half plane, but it must avoid that pole, right? Right? So this way you should be able to explain each and every entry here, right? So now let's get to the how will we prove this result delta of t. So how should I do that? Laplace transform of delta, right? Delta of t, and then evaluate at s. So the integral must be from minus infinity to plus infinity, then delta of t, then st, then dt. Tell me which rule, which property of Dirac delta do I need to solve this integral?
Shifting.
Shifting. That means that the function multiplying delta only matters where the delta is. And where is delta? T is equal to 0, right? So that function minus st only matters at t is equal to 0. Just shifting property. I don't care about the integration. So I get 1, right? How can you explain this one? Tell me. What will be your line of reasoning? The plot will look like, in time domain, the plot of this function will be look like that. And what will be there on that side? 0, right? Because of this. So that makes it which type of signal?
Right.
Right sided, but not left sided. That's the first thing. What is the second thing? So it means that the ROC must be a right half plane, but it must avoid all the poles. So it must be to the rightmost, to the right of the rightmost poles. Where are the poles? Tell me.
सर ये बहुत ज्यादा कंफ्यूजिंग हो गया, अब समझना इसको ना.
कौन सा? नहीं तो मैं तो रूल्स, आपको रूल्स देखने पड़ेंगे ना, प्रिंट करके सामने लगा देना. Actually, you're not used to these kinds of questions.
Yes,
So,
यही सर, यही तो प्रॉब्लम है.
तो
सर
ये
वो
प्रॉब्लम आपको सॉल्व करना पड़ेगा ना.
सर ये चैट में कह रही शायद
Sorry?
क्लास सही हो गया सर, ठीक है सर, सिर्फ क्लास का टाइम भी हो गया.
ठीक है, सही है. But you need to have this in front of you. आपको पैरेलल थिंकिंग करनी पड़ेगी, ठीक है. ये वो उस टाइप की क्वेश्चन नहीं है कि आप जो है ना वो फार्मूला लगा देंगे और डज. So you're not in college anymore. ठीक है.
जी सर, ठीक हो गया सर.
कॉम्प्लेक्स थॉट प्रोसेस डेवलप करें इसके बाद. ओके.
सर अगर क्लास डिसमिस्ड है तो कुछ क्वेश्चन है पूछना है?
पूछ ले मतलब मैं रिकॉर्ड.
सर वो डिसमिस कर देना पहले, फिर वो टाइम आ तो.
क्या डिसमिस करूं?
हाँ बस ठीक है. अच्छा सर वो क्वेश्चन ये था कि